Welcome to the fourth lecture of module 2 of the course called Game Theory and Economics. Before we start the topic for today, let me take you through what we have discussed in the previous lecture. What we have discussed in lecture 3, that we have given the specific definition of Nash equilibrium, which is a solution concept in game theory often used, and we have given some examples in which Nash equilibrium can be found. For example, we have talked about prisoner's dilemma and we have looked at the Nash equilibrium there. There was one single Nash equilibrium. We have to also said that in situations like battle of sexes, there are two Nash equilibria. So, we have multiple Nash equilibria. We have seen that in situations like matching pennies, which was a zero sum game, in matching pennies there was no Nash equilibrium in pure strategy. And also we have talked about the stag hunt case, and in stag hunt case, in that generic case, again there were two Nash equilibria, that is multiple Nash equilibria. What we are going to do today, and we have started doing this in the previous lecture itself, is that we are going to present a variation of the prisoner's dilemma to bring out what is the basic essence of prisoner's dilemma situation. What is it that is generating this bad kind of equilibrium? Because if you remember, in prisoner's dilemma the game looked like this. Here is player 1, suppose C, confess, NC not confess. Similarly for player 2. So, this was the game theory, the prisoner's dilemma game that we were discussing in the previous class, and we saw that there was a unique equilibrium, which is this one CC, which is a bad situation compared to this NC and C, because if both of the players had played NC, then they could have get 2 each, whereas in equilibrium they are playing one C and C, and from which they are getting 1 and 1. Why 2 and 2 are not payoffs which they could get in Nash equilibrium? Because if one knows that player 2 is going to play NC, in that case if one plays NC he gets 2, but if he shifts to C he gets 3, which is better. So, he will shift. And similarly for 2 also, if 2 knows that if 1 is going to play NC, 2 is not going to play NC, he will play C. So, ultimately both of them will play C and 1 1 will be obtained. The exercise that we are going to do today is trying to address this point, that in prisoner's dilemma the players are concerned only about their own payoff, and that is why maybe they are trying to free ride, and we are getting an equilibrium which is at CC, but which is not a good thing. I mean, they could have done, both of them could have done better if they had played not confess. And the exercise is the following. It is this: each of two players has two possible actions, not confess and confess. Each action pair results in the players receiving amounts of money equal to the numbers corresponding to that action pair in prisoner's dilemma game. The players are not selfish, rather the preferences of each player I are represented by the payoff function MIA plus alpha multiplied by MJA, where MIA is the amount of money received by the player when the action profile is A, J is the other player, and alpha is a given non-negative number. Player 1's payoff to the action pair not confess, for example, is 2 plus 2 alpha. So, first question that is being asked is that formulate a strategic game that models this situation in the case of alpha is equal to 1. Is this game the prisoner's dilemma? So, this is the question. We are basically considering one variation of the prisoner's dilemma game, and the question is the following. In prisoner's dilemma game, suppose each player's payoff is solely dependent on what the other player is getting. Model this situation as a strategic game and find the Nash equilibrium or equilibria. Is the game same as the original prisoner's dilemma game? So, to solve this question, let us first remember what was the basic structure of the prisoner's dilemma game. I am writing down the payoff matrix. So, there are these two players, player 1 and player 2, two prisoners, and they have two actions to choose from, either to confess or not to confess. Now, if both of them confess, they get 1 and 1 represented by these numbers. If both of them do not confess, then basically the guilt is not proven and they get better payoffs 2 and 2. If player 1 confesses and player 2 does not, then player 1 is freed. So, he is getting a higher payoff, but in that case player 2 goes to jail for a larger prison term. So, player 2 is getting 0, the worst possible case for player 2. And if player 1 does not confess and player 2 confesses, then player 2 gets 3 and player 1 gets 0. So, this was the original structure of the prisoner's dilemma game. What we are interested in this variation is a following situation where player 1's payoff is solely dependent on what the player 2 is getting and vice versa. So, player 2's payoff is not dependent on what he is getting, but what player 1 is getting. So, in the variation, what we shall have is that following: we shall have u 1, which is payoff to player 1 if he does not confess, but player 2 confesses, then we know that in the original game player 2 is getting 3 here, and that is the same thing that player 1 will get in the new game, which is 3. And this 3 will be obtained by player 2 if player 2 does not confess, but player 1 confesses, because we know that if player 1 confesses, player 1 is getting 3, which is same as player 2 is getting in the variation. So, this is one. Then we have just the opposite case. Here what is happening is that player 1 is confessing. So, in the original game he should have got 3, but since player 2 is getting 0 in the original game in this particular action profile, that is what player 1 gets in the variation game. So, player 1 gets 0 here. Similarly, if player 1 does not confess, player 2 confesses, then player 2 is the player who is getting the most out of the situation, which is basically 3, and that is the, but player 1 is getting 0. So, player 2 will get 0 in this variation. These are the symmetric cases that when CC is played, that both the players are confessing, then each player gets the same payoff, which is 1 in the original game, and which remains the same in the variation also. And similarly, if both the players do not confess, both the players get the same payoff, and if we flip that payoff vector, it remains the same 2 2. So, that is why u 1 NCNC is equal to u 2 NCNC is equal to 2. So, these are the payoffs that will be there in the variation. These are the payoffs, and we have to specify what are the other elements of this particular game. So, the players are same as before, player 1 and player 2, basically 2 prisoners. And actions we have to specify same as before. So, confess C or not confess NC. So, this is the basic setting of the variation. So, let us now try to draw the payoff matrix of this variation. Now, what we have to remember by looking at this structure is that when the players are taking the same action, that is CC or NCNC, their payoffs in the variation will be same as their payoffs in the original game. So, we shall have 1 1 as the CC action profile payoffs and 2 2 as the payoffs of the NC action profile. What will happen is that if one player plays C and the other player plays NC, then the payoffs will just flip compared to the original game, because my payoff depends on your payoff in the original game. So, my original payoff in the original game does not matter, it is the payoff of what you are getting in the original game that matters. So, how will this look like? So, CC payoffs are 1 1, NCNC payoffs are 2 2. CNC payoff in the original game was 3 0, now it will become 0 3, and NCC payoff which was 0 3 in the original game now will become 3 0. So, this is the payoff matrix. All right. So, now please remember what the original question was. Model the situation as a strategic game and find the Nash equilibrium or equilibria. We have to find the Nash equilibrium. Is the game same as the original prisoner's dilemma game? Now, Nash equilibrium. So, basically we are considering Nash equilibrium in PO strategy. There are 4 action profiles that we have to consider, and considering those action profiles we have to see whether deviation by any player can give that player a better payoff. If it can give the player a better payoff, then that action profile is not Nash equilibrium. Okay. So, let us consider all these action profiles one by one. CC. Now, from CC action profile we can see that both the players have actions which are better than what they are playing in this CC profile. So, if player 1 deviates and chooses NC, she gets 3, whereas in CC one gets 1. So, for player 1 playing NC is better than playing C. So, for 1 playing NC is better than C, and this is true for the other player also. For player 2 also we can see that if player 2 plays NC, she is getting 3, whereas in CC she is getting 1. So, deviation is profitable for player 1 also, deviation is profitable. So, CC is not Nash equilibrium. So, that is what this exercise of CC is telling us. Let us consider another one, CNC. If we consider CNC, basically we are talking about this payoff vector. Here we can see that from CNC player 2 does not have any profitable deviation, because what player 2 can do is that player 2 can play C instead of playing NC, but if he plays C, he is going to get 1, which is worse than 3. So, for player 2 there is no profitable deviation from CNC. So, that is there. So, player 2 will not deviate, but for player 1 there is profitable deviation from C to NC. Let us see this. If player 2 is playing NC and player 1 is playing C, player 1 is getting 0. But if player 1 deviates and plays NC, then player 1 will be getting 2, which is better. So, there exists a profitable deviation, and therefore, CNC is not Nash equilibrium. So, CC got ruled out, now CNC is getting ruled out. Similarly, we can show that NCC is not Nash equilibrium. NCC is this one. Here player 1 does not have any profitable deviation, but player 2 does have a profitable deviation from C to NC. So, therefore, NCC is not Nash equilibrium. The last one we are left with is NCNC. What about NC? Now, it is not necessary that every game should have a Nash equilibrium in pure strategy. It might very well happen that there is no pure strategy Nash equilibrium. So, let us check whether NC is a Nash equilibrium. We are talking about this cell here NC, giving each player 2. Now, if player 1 deviates and plays C, then player 1 will be getting 0. If player 2 deviates to C, then also player 2 will be getting 0 instead of 2. So, deviation from NC by each player reduces that player's payoff, and therefore, this NC that we are considering here is a Nash equilibrium. Deviation in fact reduces payoff for each player. So, that is the answer of the question. The last part of the question was is the game same as the original Prisoner's Dilemma game? No, this is a very easy question to answer. It is not same as the original Prisoner's Dilemma game. This was the original Prisoner's Dilemma game, right? And here what we are getting is this, and what we are getting in this changed game is that the payoffs in NCC and CNC in these two cases have changed, and because of the change in the payoff in these two cells, that is CNC and NCC, the game does not remain the same obviously, because the payoffs have changed. Moreover, the Nash equilibrium of the original game no longer remains the Nash equilibrium in the changed game. In the original game, this was the Nash equilibrium CC. This was not the Nash equilibrium, right? And we have seen that this is a kind of Nash equilibrium which is suboptimal for both of the players. They are getting less than what they could have got if they had both of them had moved to NC. But here in the variation, this CC, the suboptimal outcome, is no longer the Nash equilibrium. What we are getting is that NC is the Nash equilibrium. So, in the changed game, the payoffs have changed, and Nash equilibrium has also changed. Therefore, so the game obviously has not remained the same. So, that is it. The game has not remained the same. The Prisoner's Dilemma game that was there in the original case, that has changed in this changed circumstances, where each player's payoff is dependent on solely on what the other player is getting. And curiously, what we are getting here is that in the original game, when players were only considering their own payoffs, we had a suboptimal Nash equilibrium at CC, where the payoffs are not the maximum payoffs what they could have got, but when they are being sort of altruistic, when they are considering other players payoff as their own payoff and they are ignoring their own payoff, in that case the Nash equilibrium that is emerging is that equilibrium, is that outcome where payoffs of both the players are maximum. So, that is it. This is an exercise where we are trying to answer this question: is altruism always good? Okay. So, let me first write down the question and then we shall try to solve this question and try to see whether altruism always gives us the best outcome. Okay, so this is the question. Let me read out the question before we try to solve this. Two Nawabs are waiting to board a train at Lucknow railway station. Out of courtesy, each wants the other to board the train before him. Boarding later is considered better than both boarding early. If both keep on waiting for the other to board, the train leaves. However, boarding the train before the other Nawab is considered worse than missing the train. Missing it is worse than both boarding early. Model the situation as a strategic game and find its Nash equilibrium. Does the game resemble any game studied before? Okay, so what we are having here is that there are two Nawabs. So, players are two Nawabs, let us say 1 and 2, player 1 and player 2. Actions, what are they doing here? Either boarding the train early, we shall call it, let us say E, or late, we shall call it L. So, there are two actions. What about the payoffs? Here we have to be careful. What is best for, let us say, player 1? Let us look at the question once more. Out of courtesy, each wants the other to board the train before him. So, if I board it later than the other player, that is good for me. Boarding later is considered better than both boarding it early. So, this is the other thing, that both are boarding early, that is EE, that is worse. However, boarding the train before the other Nawab is considered worse than missing the train altogether. Basically, if both of them are waiting for the other to board it early, because basically both of them are choosing late, then the train leaves the station. So, that is another outcome, but that is considered, that outcome is considered better than boarding the train before the other Nawab. So, basically what we are saying is, here we have four outcomes. One is E L. So, first player is choosing early, the second player is choosing late. Another could be both of them are choosing early. Another could be both of them are choosing late, and another could be both of them, first one is choosing late, the second one is choosing early. Now, for player 1, what is best is this one, this is rank 1, because he is choosing late, the other is choosing early. So, that is how that is the pure courtesy which is shown by player 1. Second one is both of them are choosing early. So, this is 2. Okay. Third one could be both of them are choosing the late, when in that case the train basically leaves the station, none of them can board the train. And the fourth one, which is the worst possible for player 1, is he has boarded the train early and the other Nawab has boarded the train late. Out of courtesy, he considers this to be even worse than this, that if I board it early than the other Nawab, that is considered worse than both of them missing the train altogether. Because in the latter case, when both of them miss the train altogether, at least I have shown courtesy to the other player. So, that is considered very worthwhile. So, this is how the outcomes are ranked by player 1, and let us give them some numbers. So, here I have 3, 2, 1, 0. So, this is for player 1. Player 1 is considering that outcome the best, where he boards it late, the other Nawab boards it early. The second best is both of them are boarding it early. Third is both of them boarding it late, in which case the train leaves. And fourth is he boards it early, but the other Nawab boards it late. So, that is worst. This is for player 1. What about player 2? For player 2, obviously it will be just be the opposite. For player 2, boarding it late than the other Nawab is the best. So, he will give EL the highest payoff. Okay. The second highest payoff will be when both of them board it early. The third highest is both of them boarding it late, and the fourth highest is that he is boarding it early and the other Nawab is boarding it late. That is the discourtesy shown to the other player. So, these are the payoffs then, and let us try to look at the payoff matrix and try to find out the Nash equilibrium. So, this is the payoff matrix. For player 1, the best is I am late, the other player is early, and the worst is I am early, the other player is late. Second best is both of us are early, and the third best is both of us are late. Okay. And the opposite for the other Nawab. So, this is the payoff matrix in this game. Okay. Now, what we are having here is that this in this game, what are the Nash equilibrium, that we have to find out. So, we follow the usual method of finding the Nash equilibrium. We start with any arbitrary action profile, let us say EE. Now, from EE, is deviation better? Obviously, it is better. Both players have profitable deviation. This is easy to see because if player 1 deviates to L, he is getting 3. If player 2 deviates to L, he is also getting 3 instead of 2. So, deviation by each player is beneficial. So, therefore, EE is not Nash equilibrium. What about, let us say, EL? So, we are looking at this action profile EL. Here player 1 has a profitable deviation. 1 has profitable deviation. Okay. Essentially what is happening is player 1 is choosing early, player 2 is choosing late. So, player 1 is being discourteous here, and that is why he is getting 0. In this case, what he will do is that rather than boarding the train early, he will also wait for the other player to board, and so he will get 1, but obviously In this case, both of them will miss the train. So, that is, so EL is not a Nash equilibrium. Not Nash equilibrium. Similarly, we can show LE is not Nash equilibrium. And finally, what is left is LL. Okay. LL is a Nash equilibrium, because from LL nobody basically tries to deviate, because if anyone deviates and boards the train early, he is being discourteous and that is worse. So, therefore, LL is a Nash equilibrium. In fact, it is the Nash equilibrium, okay, because no player can deviate and improve her payoff. So, this is the only Nash equilibrium. There is a third part to the question: does the game resemble any game studied before? Well, yes, this game is just like the prisoner's dilemma game, because what we are having is a Nash equilibrium, the Nash equilibrium, where each player is getting less than what he or she could have got if they had played some other action profile, which is like here 2 EE. In this case, each player would have got 2, but that is not a Nash equilibrium. E is not a Nash equilibrium, we have seen that. So they are basically left with a Nash equilibrium which is worse for both of them. So, that is it. So, let me conclude here. Thank you. What is the Nash equilibrium in Battle of Sexes game? Elaborate. Let us go back to the payoff matrix of Battle of Sexes game. So, this is how the payoff matrix looks like, and what is the Nash equilibrium? We shall see that there are two Nash equilibria here. One is BB and the other is OO. Payoffs, it is 2 1 and 1 2. What is why is this a Nash equilibrium? Because if let us consider BB, from this profile, if player the wife deviates to O, she gets 0. If the husband deviates to O, again she gets 0. So, there is no reason why they should deviate. Similar logic applies to the OO profile as well. So, both of these are Nash equilibria, and we can similarly show that neither BO nor OB are Nash equilibria, because from them we can have what is known as profitable deviation. Is matching pennies in matching pennies and stag hunt game, what are the Nash equilibria? In matching pennies game, this was the payoff matrix. And we can see that there is no Nash equilibrium in the matching pennies game. For example, let us start with this HH. From here, player 1 will have profitable, sorry, not player 1, player 2 will have a profitable deviation, because player 2 is getting -1 in HH profile, whereas if she plays T, she gets 1, which is greater than -1. But is HT a Nash equilibrium? No, because player 1 then will have a profitable deviation here, because he will get 1 here, whereas he is getting -1 here. From here again, player 2 will have a profitable deviation, and from here player 1 again will have a profitable deviation. So, basically there is no Nash equilibrium. What about stag hunt? In stag hunt, there are 2 hunters. This was the game, and we shall see that Nash equilibria are there. There are in fact 2 Nash equilibria, and these are ST-ST and HH. From ST-ST there is no profitable deviation, neither is profitable, and similarly from HH also there is no profitable deviation, because if someone deviates, for example, if player 1 deviates, she is indifferent between playing ST or H. In either case she is getting 1. Similarly for player in this case player 2 is deviating. If player 2 deviates, she gets 0, which is worse. In this case player 1 is deviating, and if she deviates, she gets 0, which is bad, which is worse. So, this is not a Nash equilibrium, neither is this a Nash. So, this is 1 is a Nash equilibrium, and 2 is also the payoffs in the Nash equilibrium profile. Third question, find the Nash equilibrium of the following game. If we look at this game carefully, we shall find that there is a single Nash equilibrium, which is here, which is basically dm. Why? Because from dm, if player 2 deviates, she can deviate to r where she is getting 0, which is worse. She can deviate to L, which is again worse, which is 2. If player 1 deviates, she can deviate to U, and she is getting 2 here, which is worse than 3. So, no profitable deviation is there. We can verify that for other profiles there are profitable deviations. For example, let us take this. From here player 2 can deviate profitably. From here, let us take this profile UL. From here obviously player 1 will deviate. So, the only Nash equilibrium is dm, where the payoff is 3, 4. So, that is the end of the exercise. Thank you.